All right, hello everyone. In this video, we're going to be looking at an analysis of a truss using the method of joints. And I think this is going to have to be broken into two videos because it's kind of long, so I'll do the explanation in this video, and the second one will be an example. And then in the video following that, we'll do a separate method called method of section. So we're going to spend some time on these. But let's start by defining what a truss actually is. And you can kind of see here's a representation of a truss. Where we have these little gusset plates and things. But when we actually analyze these types of trusses, what we're going to be doing is we're going to be replacing those plates with like a pin at each one of these connections. And what that allows us to do is make everything two force members, if you remember what those things are. So it makes the analysis much easier. So let's go ahead and define what a truss is. So in order to be a truss, the only thing we can have are straight members connected at the joints. So for instance, we can see between like A and B, this clearly is just a straight member, and it's only connected at those joints. Second, that's the second piece of it, is it can only be connected at the joints. So for example, if we were to look at this, something like this truss on the bottom, we couldn't make this bottom member one member and call it like member AB and just have it connected in essence three places, like once here, once in the center, once in the end, because it would no longer be a two force member. So the only way we could have that truss is if we had two separate pieces, this BD and also AD and then CD, and that way each one of those members are only connected at the ends. So like I said, what that does is it creates a series of two force members. Let me put a couple of little things in here. We cannot have any loading other than at the joints as well. So as we can see here, we put this load at P, but it's happening at the joint. It would not be valid to put a load here or here, but I could put a load here. So, and once again, it just plays into the fact that if I did put one here, I'd no longer have a two force member, but as long as it's at the joints, it still acts as a two force member, which makes this analysis valid. Another piece is that they have to be pinned connections. All of these connections are pinned. And the point behind that is if we have a pin here, we know that a pin can handle reaction in the X and Y, but there can be no moment, right? So that way we're still with this whole two force body thing. And what all of this leads to is that each member is going to be a two force body in either tension or compression. And as a reminder, what that means is if I have a member and I'm pulling on it in both directions, it is in tension. I think these are all terminology that you should be familiar with by now, but just in case. Of course, the opposite, if I'm pushing on it, would be in compression. And each one of these members can now be thought of as either being in tension or compression, and the force has to be along the members themselves. Let's talk a little bit about the number of pins and joints and members I actually need to be a simple truss. So I think everyone has seen an example like this, where if I had 4 pieces connected together, this technically meets all the requirements. I don't have any loads other than at the ends of each member. Everything's straight and everything else. However, if I were to look at some external force on here, hopefully you can see this whole thing would collapse. So this is no good, right? How would we fix that situation? We would have to add some other kind of member. And you could actually add a diagonal member in either way, but I'd have to add something to handle this lateral force to make it good. So I guess I take away that no good now, right? So if we were to look at how many members and how many joints we need, there is an equation for that. I'm just going to jump right into the equation. You can verify this, I suppose, on your own. The number of members needed is equal to 2 times n, which is the number of joints, minus 3. So m is your number of members and n number of joints. So if you have a case where you have your number of members is less than 2 times n minus 3. That was that first case we talked about where it's just kind of hanging out there. We call this unstable, meaning it can collapse at any particular point. We don't like that as engineers. On the other extreme, if we have m that's greater than 2n minus 3, what that looks like is if I were to put a diagonal here, then we're stable, nothing's going to happen, and everything's fine and dandy. What if I were to put yet another one in here? What happens is it's still stable, but it's statically, we can't actually solve for this thing. So we're going to call this statically indeterminate. And if it's statically indeterminate, then it is not what we're calling a simple truss, and we will not have it. We'll not analyze it in this class. And here's an example of a whole bunch of bridges that I pulled up. And you can spend time on there if you want. Nothing too excited. Let's go ahead and verify that it actually works. If we were to look at, we can look at any of these. Let's look at the Pratt. How about, see if I can do this and count up my n in my m's, right? So let's start with my m, my number of members. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 if I did my math right. And my number of joints, do that in blue so I can see it. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then looking at our equation then, is it true that 21 is equal to 2 times 12 minus 3? And that would be, what, 24 minus 3, which is equal to 21. So we have, yes, confirmation that that is actually a simple truss. Yeah, so I guess that's all I have to say about that. Let's talk about the process of what we're going to follow when we're doing these problems. The first step in this method of joints is to solve for your external reactions. So, for example, if I were looking up here and I had some kind of loading on this Baltimore, like say I had some loads up here, first step would be to figure out what's going on at these pin and roller connections. That's what I mean by external reactions. External meaning they're not internally to the force. It's just your connections, right? We've done that before. Second step, what you're going to do is you're going to pick a joint. And usually you're going to pick a joint right at one of those connections. And you're going to draw a free body diagram at a joint. And there's no real particular rhyme or reason on which side you'd start on, but typically you'd start on one. You know, why would you start in the middle? After you pick this joint, then you're going to solve for the forces along the members at that joint. So, for example, I guess I'll take this Baltimore since that's what I was just doing anyways. If I were to look at, say, this joint right, I don't know, let's look at this joint right here. If I were to call that like joint A, then I would have something like joint A. I already have my external reactions, which I want to leave in there. Whoa, external reactions. And then I also have internally, I'd have these two other forces. And because I know they're two force bodies, I know the direction they're headed. So I'd have one going this way, and I'd have one going that way. And there's a little something else, and we'll talk more about this when we do an example, but I do know the direction of these arrows because I know I'm going to have some of the forces in the y direction equal 0, right? It's all in equilibrium. So now that one's actually going to be pointing towards the node. And I also, or towards the joint, and I also know the other one. Actually, I don't necessarily know the other one, do I? But I would probably think that it's pushing this way. So, and then I can use my sum of the forces in the x direction equals 0 and sum of the forces in the y direction equals 0 to solve for those two unknowns, because I have one unknown here, and I don't know, I don't have these things labeled, but this might be like AB and this might be like BC if this were joint B or something. But whatever it is, a couple hints for solving all of these forces along the members. First thing is, I said I know that it's pointing towards the joint. Well, what that means if it's pointing towards the joint is that member is in compression. And of course the opposite is true if your force points away. And, you know, I think it's easy just to remember that and just get used to it and go with it. If for some reason you forget or you doubt yourself, this is kind of why it's happening. Is if I had a force that's pointing towards the member, that means it has to have an equal and opposite force that's pointing on my member. And we said that member would be in compression because both ends are pushing. So, and then the same with the opposite. If it's pointing away from a joint, then it means the member is pulling equal and opposite, so that member has to be in tension. So maybe that diagram helps. Maybe it's just easy to remember. Pointing towards is compression, pointing away is in tension, or whatever floats your boat. The other thing that will really help you out is this idea of your components using the length of each side. So we're going to use the force of each vector in the y direction, or each force in the y direction is equal to the total force times the y distance over the hypotenuse, and in the x direction, x over the hypotenuse. Meaning, if this is vector AB, and I know that vector AB is on this truss, what do we mean? Like say this is the one we were looking at. Well, I know that this is my length of the vector, this is my x direction and y direction, right? So what I end up with is that when we look at this AB, and I'm using this x, y, and z, x and y summation of forces, this is my x direction, my y, and my length, and that's for the entire vector, right? So maybe let me draw it a different way because that kind of came out like garbage. So let's say I have a member here, and I want to know its force, and I know the force is along here, right? And I can figure out this member's total length because I know how far it is in the x and the y direction between these two pinned connections, right? And this is its length. And this is my vector, I don't know, I'll just call it force. Then I know that this force in the x direction would be equal to the x distance over the hypotenuse, and in the y is equal to y distance over the hypotenuse. It's nothing new, it's just get really used to doing that. You could potentially find your angles inside here and use your sines and cosines, but trust me, you'll get killed trying to do that in any kind of timely manner. So if you haven't gotten used to this, get used to it, because it'll definitely save you time. Once you do it once or twice, you're like, oh, okay, I kind of get this, and then you'll fly right through it. After you do this and you solve for your forces in these two members that we just drew, then you're going to go to your next joint and repeat until you have all of your forces. So, and I don't know how often that takes, and what happens is typically, oh, I need to go all the way up to 2, don't I? Typically what happens is you end up backtracking, so you might actually be able to double check work at some point, but you'll see that in the example we'll do in just a bit. Thanks for watching, and check out part 2.